Okay, we are now doing gas lecture number 7. So we just finished up with problem 11A. Looking for my problem worksheet. There it is. Okay, so 11A said what happens if the Kelvin temperature was doubled. And then, so just quickly to point something out, 11B said, what if the temperature was cut in half? So with all of these problems, you'll definitely want to make sure that you always do the equation setup and answer. So 11B, you're going to do the formula. There's Charles' law. Notice the temperatures are always in Kelvin. And you have everything set up, and you can cross multiply now and solve this. So we took a little bit of a liberty here because since we're cutting something in half, that's a math function. So you can put down the exact number for that. No reason to round that because it's a mathematical function, and you're just cutting it directly in half. Okay, so again, multiply these, divide by the 1 on the opposite end. If you think about this, we're just bringing the 136.5 over here on the top, so you multiply them and then divide by what's on the bottom. Make sure that when you crunch those numbers that you are getting 5, which is what we expected, direct relationship. If you cut it in half, you're going to cut the volume in half too. And that's exactly what happened. In paying attention to sig figs, instead of writing 5 or 5.0, these have 3, so we're going to put 5.00 meters cubed. Again, that's just, that one final point on these problems. There's lots of points here, but just pay attention to the sig figs. Okay, so this lecture is mainly emphasizing the combined gas law, where we're going to do everything together. For problem number 18, you're going to be doing something called Amonton's law. And Amonton's law is if you leave the volume out of it. So that's pressure over temperature equals pressure over temperature. It's not as common of a law, but you can see these are also direct relationships. Okay, and you could have an effect on the temperature if the pressure increases enough. You can get those molecules start to increase the average kinetic energy and increase the temperature. So again, a direct relationship. But you'll need this equation for number 18, which we're going to get to, but I just wanted to point out that there is another law called Amonton's law. Okay, so at this point, I would expect you to be able to go through and do numbers 12 and 13 and get the correct answer. So really make sure you're working on that. That's our assignment. You have the answers. Now I just want you to prove to me that you can go through and get those answers. Now, number 14 is pretty straightforward. You have to know what STP is to do these problems, and know what the standard temperatures, know what the standard pressures are, and apply those in setting up number 14. But I really want you to work through those, make sure you're crunching the numbers. We're going to do 15A together because it's a little more challenging, and I want to make sure you know how to set this one up. And by doing 15A, that's going to help you with 14 and 16 and 17. Okay? So so you can see right now our goal is to do all the Charles law problems and all the combined gas law problems. So let's take a look at A. It says the following gases are collected over water. Red flag, remember? or actually blue flag, blue sheet, blue reference sheet, because they're collected over water at the given conditions. And it says calculate the volume occupied by the dry gas at standard conditions. All right, so what it gives you is 200 centimeters cubed of oxygen at a temperature of 15 degrees Celsius and 94,000 pascals. All right, so first thing you saw that it was collected over water. So then you're like, well, it's oxygen gas. There's my water vapor. It said it was at 15 degrees Celsius, so I'm going to look that up on the blue sheet. The pressure total, you want to change the 94,000 into 94 kilopascals. Easy conversion there. You did some of that when you did your Boyle's Law problems. So that's the total pressure. I need to fix the pressure of oxygen by realizing that there's a little bit of pressure caused by the water because you collected it over water. And then you solve that. Watch your sig figs. This is 0 places to the right. So this one should have 0 places to the right, rounded to the nearest whole number. So 92 kilopascals is as accurate as you can get with that initial pressure. Now, we take that pressure and we're going to plug it in. That'll be our P1. And it said it wanted to convert over here to standard conditions. Well, I now know what this is. That's 92. That's a given. The 2.00 times 10 to the second, I'm just going to write as 200 with a bar over the 0. You could write 200 with a decimal point. But just make sure you know that those are all significant. This, however, is 2 sig figs, so that's going to limit our final answer. 288, where did I get that? Think about that. Look at problem 15a. Yes, 15 plus 273. You need to add 273 to every temperature. So that's where the 288 comes from. Now, you're going to convert this into standard. It wants to know what volume would it be at standard conditions. And by the way, B and C and D are similar problems to these. So you can do a couple more, do these on your own and figure out if you're understanding this. So the standard pressure is in kilopascals is 101.3. That's something you have good notes on. You can look that up. Whoa, what's standard pressure if it's kilopascals? Because this guy's kilopascals. And hopefully the temperature, without even looking up, is 273. Okay? Now, how you do the math here is very important. I always, in my mind, I just say that 273 is going to slip up on top over here. So I multiply these together. That gives you your cross multiply, right? So you're going to multiply all these numbers. Now this 101.3 is going to drop down on the bottom with this 288. So the way I do these problems is I take 92 times 200 times 273 equals. That's the numerator. And then I go divided by 288 equals. Divided by, because that's going to slip down to the bottom, divided by 101.3, hit the equal key, and bottom line is just make sure you're getting that as an answer. Now that's not what your calculator is going to say, but you need to round it to 2 sig figs because of that 92 right there. Okay, so we're really getting to practice with these significant figures. All right, so that's a two-part problem, just like when we did the Boyle law, Dalton law. No, this is combined law, Dalton law, and that's what number 15 is. Number 14 doesn't say anything about collecting it over water, so you can just plug the numbers in and solve and see if you're getting those right answers. Now, you're going to struggle a little bit. You're going to be like, that's not the answer I'm getting. Again, I'm 90% sure that the key is correct on these. but let me know if you're struggling on these. Okay, I want to do one more. That was 18. I said 18. Now, if you look at 18, it says an automobile tire has a pressure of 210 kPa at 20 degrees Celsius. Usually we use PSI with tire pressure, but this one has 210 kPa at 20 degrees Celsius. And then what would be the tire pressure if it rises to 35 degrees, so it gets all warm on a summer day on the black tar? How would that affect the pressure? Well, temperature goes up, pressure goes up. We said that that's a direct relationship. So this is where you use, you can think of it as the combined gas law with the volume being constant, because it's a tire, right? And so you can leave the volume out of the equation and use Aminton's law. So P1 over T1 equals P2 over T2. And initially, we had this pressure in kilopascals. Again, add 273 to the Celsius temperature. Really, really hammer that in your head, okay? And then over here, they said what would happen if you increase the temperature. So we're up to a balmy 308 Kelvin. And that is, of course, going to slightly increase that pressure, because this is a direct relationship. So this is going to go up. You're going to punch those numbers in your calculator. So again, just to be clear on this, just cross multiply and take 210, and you don't have to even hit the 0.0. You can worry about sig figs at the end. Times 308, and hit the enter. And now divide by the 293, because that's going to be on the bottom, right? Divided by 293. Now this says that the answer is 220.750853. Well, how many of those are significant? It's going to be just 3 of them. So 220.7, you round to 221 kilopascals. You check your answer for number 18, and it's 221 kilopascals. Okay? So you can continue to do this. Here's what you need to have done to be caught up. All of the problems, 1 through 19, you should be pretty comfortable with. If you're having problems with any of them, we need to email or set up a Google Meet or ask questions in class so that we can get that fixed, all right? Because this test is going to sneak up on us next week before you know it. As you can see, we're almost all the way through, and after tomorrow, we're going to be done with this whole worksheet. So make sure that you can do all of problems up through 19. We've done a good chunk of them together, but it's really important that you do them independently. That's what's going to happen on the test. All right, you're going to have problems just about identical, and you have to kind of recognize how those are set up. Okay, all right. Have a joyous Thursday evening, and we will see you tomorrow, same time, same channel.